In this video, we're going to talk about pool type structures where we have sunken slabs and how to model those with and without post-tensioning in ADAPT+Builder. So in this example, we'll be using Edge with Floor Pro. We're going to have the option to include post-tensioning, and we'll use US unit system. The first thing to note is that by default in the program, if we go to a side view or a front view, we can see that there's three default planes. There's current, bottom, top. The default in US units is 10 feet or 3 meters in SI units. So we're going to have a structure where we might have a column, and then we have a slab, and this slab may do something like this, where we have some deep offset here, and the beams that are forming out the sides of this pool might also be supported by columns. And it's important to understand how we can model this. This member here can either be a beam or a wall, but there are certain limitations to both modeling types. So we'll go ahead and get started. We'll go back to a plan view. I'm just going to set up a simple grid using our grid settings here. I'll do a 10 by 10 foot grid in this case. And then we'll go ahead and set up a slab. Now the slab for the pool, we're going to go to model and slab, and we're going to, everything here is going to be modeled referenced from the current plane. And we're going to assume that there's a 4 foot offset. So we'll do a 40 foot by 80 foot slab, and that looks like 80 there. We'll just assume that that's 80. And then we're going to model another slab around this slab. So I'm going to take this and just wrap this around. This might be, for example, a pool deck. And I'm going to wrap it around this slab that we've already drawn for the pool. And then I'll go back and just model the other side as a third slab, something like that. This slab on the interior is going to be dropped by 4 feet. So we're going to go to the properties, and I'll use a vertical offset downward, which is positive 48. Okay, if I go back to a side view, we have something that looks like this. The next step is we're going to add some columns. So I'm going to add a column. We'll make these columns 20 by 20 square. And we'll do a grid that looks like this. It's 40-foot grid. We'll go ahead and save this. I'll turn the snap grids off, and now I'm going to model some beams. So the way we want this to behave is we want a top slab, and then we're going to create a beam, which is referenced here, and then we have a bottom slab down below. Now the distance from here to top of the slab is 48 inches. So for the beam depth, we need to add in the thickness of the slab on the base of the pool. We're going to call that, we're going to call this slab 10 inches. I'll make this slab 10 inches. And then the pool slab will also be 10, and the beam will be 58 inches, and we'll say a 12 by 58 beam. So we're going to go to the beams. The properties of the beam will be 12 by 58. I'll turn on the snap to endpoint, and now I can model the beams along this interface. Okay, something like that. If I go to a side view or a 3D view of this, we have this type of a configuration. Now, one very important point here is the location of the beams relative to the column. This column will be discretized into 2 frame elements, 1 and 2, which will be broken at the midpoint of the column. Midpoint is established from the reference plane, top and bottom. This would be the bottom reference plane, which is called bottom plane, and the top reference plane of the column is shown here, top. So if the node, and I'll put the node in pink, if the node of the column is below the reference node or the physical node of the beam, in this case it's up obviously below this is acceptable. If this node of the beam actually is below the mid node of the column, then you could have connectivity problems and this beam really needs to become a wall. But that also imposes some limitations, which are the design strips along the beam. If I go back to a plan view like so, and I draw in support lines along here in order to design this beam, the wall would mean that the wall element would not be included as part of a section. So if I draw a design support line here and I have design cuts along here, this section would look something like this. If I replace that with a wall, which might be required in order to meet that requirement relative to the nodes that we just discussed, the design section really just looks like this. So one workaround would be, if you have a very, very deep beam and a short column height, then you could stretch the column vertically and then adjust some of the material properties to try to create an equivalent stiffness, having artificially increased the column height. So that's one option that the user can do. Now, in this case, we're working really only in single level mode. So everything that we've modeled will be referenced back to this current plane, and when we analyze it, the beam, beam creates a connectivity between the lower slab and the upper slab, and we have proper offsets defined relative to the beam elements, and this thing should run just fine. So I'm going to go ahead now and just take a couple of cuts through here just to look at the geometry. So I'll go to Home, I'll draw a cut through this location. There's our pool, and then I'll draw a cut, let's say, through this location. This is through the columns, so everything here looks to be connected just fine. And I'm also going to load this, so I'll just grab these two slabs. These are the deck slabs. I'm going to add 100 psf of load. Live load we'll say is 100. And then for the pool slab, I'm going to say that the load there is 350 for live load. Okay, another thing about the beams that gives the user more flexibility is we can model post-tensioning in these beams. If I wanted to model some PT cables here, I can do that from tendons, add a tendon, and I can go in and model PT in these beams. We'll add a couple of tendons here. And if I go back to a side view, or a 3D view rather, I'll turn off the loads. We have our loads in place. I didn't add any superimposed dead load for this example. We'll just leave it to the live load. You can see the beams with the PT there. I'll make this 20 strands, and we might adjust the CGs here. We'll say 3, and then 3 here. Say 27 out on the ends. Something like that. I'll make the same changes here. I'll say 20 tendons and 3. Okay, so beam modeling allows the addition of post-tensioning. In modeling walls, it's a little bit different. With walls, you can still model post-tensioning, but the post-tensioning essentially becomes external from the slab. The offsets and eccentricities are still recognized relative to the reference plane, so technically modeling PT with walls will work in terms of overall behavior and analysis results, but you still are unable to obtain design section results with a wall. So, and in addition to that, because the tendon exits the slab and it's not technically recognized within the wall, you essentially are forced to use an effective force method for assuming the post tensioning in those members. So we're going to go ahead and run this example. I'll mesh this. Okay, notice that the beams are not meshed. Those are frame elements, so they're discretized when we analyze as frame elements with individual nodes, single nodes at the I and J end of each element. And then I'll go ahead and run the execution of the model. Now, just to look at the overall behavior, I'm going to turn on the deflection. So in analysis under slabs, we'll go to the deformation, and this is for surface total. And if we go to visibility and look at the rendering of this actual solution, we're going to be able to look at the deflections in these slabs. So I can turn on the Z deformation, and we can see the deformed shape. Everything here appears to be connected. I forgot to actually add a beam on that side there, so you can see it's still connected, but there's just no beam connecting the upper and lower slabs. We'll go back and add that. To look at the deflections of the beams relative to the slab, we can look at the beam diagram. So if I turn on I'll go ahead and turn off the shell elements. Now I'm looking at the slab contours, and along with the contours I can turn on the beam diagram. So if we go to beam deformation, look at the Z direction deformation, you can see that this deflection 0.15 should be compatible with the deflection of the slab at the same location, and then we get the deflection here in the actual pit or the bottom of the pool. And we have that strange result there where we don't have this kind of two-way bending over here. This just is one way over on this side because we don't have that beam connecting the two slabs. We'll go ahead and add that. We'll go back to model beam, and I'll add this beam here. And I'll need to go ahead and remesh the slab. We'll execute the analysis again. Okay, and now if we go back and check our deflections, we can see that we have some symmetry happening in this case. Now if we wanted to set up a design strip along here and maybe strips inside of the pool, those would have to be separate. So let's go back and I'll turn off my elements. To do that, I'll go to the analysis visibility panel, just turn off the shells like so, and we can add our support lines. So for the support lines, we'll go up to floor design, X direction. I'll create just X direction strips out on the deck. I'll create an X direction strip from this column, just a single span, and then I'll do strips right along the beams, and I can change those to beam criteria versus two-way slab. And then I have strips in this direction, and I also might have strips down inside of the pool slab. So I might have one. I'll do actually 3 strips down there in this direction. We're going to do another one here. I'll use snap to perpendicular, and then a 3rd strip. So this is somewhat arbitrary. We're just generating strips. We could create strips only along this frame line. I'm kind of just modeling this with unit strips in both directions, so that's how I'll approach it in this video. If we go ahead and generate our design cuts, you can see we have our design strips shown like so. Here we have a cut that actually extends from a slab that's 48 inches above a slab on the opposite side of this beam. So we want to place a splitter along the perimeter of the beam so that this doesn't encroach into this space. I'll go ahead and do that. So I'll delete the strips that were created. I'll add an X direction splitter, and I'm actually going to add that on the face of the beam from, let's say, this spot over to this spot here, and I'll do the same thing on this side. So we'll add those and I can regenerate the strips. And you can see now these cut all the way to the face of the beam, these cut over to the top of the beam, and then they stop. And from here we could go ahead and design sections, check stresses, obtain reinforcement, and so on for this system. If we look at these strips which have PT, I could go to the stress checks for the design cuts. If we go ahead and check the stresses, we can see bottom and top stress for those cuts. I can obtain reinforcement for example, for all of the other cuts associated with the slabs. And this just allows me to kind of isolate one slab versus another using my design strips. Now the same approach could be used if we had a multi-story structure and we ran this model globally or in single level. The slab that's offset down always references back up to the plane in which it is connected to, if you will. So we'll go ahead and change this model. I'm going to go back to floor design. I'll delete the design strips. Just going to go to a side view and I'll turn on the splitters and support lines. I'm also going to turn on the loads. We're going to go ahead here and add some levels to this, and I'm actually going to copy all of this up a few floors. So we'll go ahead and add additional planes, and we're going to say that this actually occurs up at the 12th floor. Okay, so I'll take all of this and I'm going to go to modify. We're going to copy and move vertical. I'm going to copy this to plane 12. Okay, so we have it up here on the top. I'll delete out the loads at this level. I'm actually going to delete out the beams at this level. And you can see it shows me that I'm still working in single level on the current plane, but it will show me where that copies to. If I go ahead and just toggle multi-story back to single level, it updates and comes back without showing what's happening at level 12. Here I can delete out some of the strips that may not be necessary. I don't technically have to remove this slab. I can just adjust the slab and just basically set the offset back to 0. So this slab is now just at the same plane. I'll select by type, support line splitters. If I wanted to remove those, I could just delete those out and redraw them if needed, or I could keep them. If we go back to a side view and multi-story, I'm going to now copy this up 10 times. So we're going to go back to modify, vertical copy. We're going to copy up 10 times. And I may have copied one too many times. So now we have a multi-story structure with the sunken slab at the top. If I analyze this particular structure in multi-story mode, the program will properly handle this situation where I have the sunken slab. If I was to model it in single level mode, if I navigate up to level 12 now, it's the similar approach as what I had just done in single level. I have the same exact essentially the same exact model as I had earlier. It just now belongs to a multi-story structure. Okay, now we're going to change this slightly. We're going to go ahead and the first thing we'll do is generate a short level here. So the level itself is actually going to be just 1 foot below this slab. So this is 58 plus 12, 70 inches in terms of the level. So we'll call that, we'll just say it's 6 feet. And if we go to Model Story Manager, I'm going to say level 12 is only 6 feet, and I'll apply that. Okay, now we have a condition where the beam and the column centroids may be in a position such that the beam is above the beam midpoint is above the column midpoint, if you will. And here we may have to shorten that just a little bit more. We're actually going to short it down to 58 inches. So 4.83 feet is what we'll use in this case. We'll make that such that it's the same as the... So we've taken care of the column duplication by just deleting each of the columns one time to get rid of the stacking column. Now, because our beam mid-height is, rather the physical node location of a beam frame element is above, below the midpoint of the column, which gets discretized also into two vertical elements like we talked about earlier, well, we need to replace these beams with walls in order to be able to analyze this properly, just due to the connectivity issues. So what I'll do is go ahead and get rid of the beams. And I'm now going to add and replace those with walls. So we'll go ahead and add a wall. I'm just going to add one wall to begin. And if I go back to my 3D view, we can see that the wall is essentially the top of the wall references level 12, the bottom of the wall references level 11, or plane 12 and plane 11. We'll go ahead and change this wall to 12 inches thick, similar to the beam. And if we take a cut through that wall, notice that the wall really should be offset downward just by a few inches there. So we're going to offset that wall vertically from the bottom downward. We're going to offset that 8 inches. If I update my cut, actually it should be 6 inches here. This is now the section through that location. So the program will retain those properties of the wall, both the offset and the thickness, based on a general setting shown here. We'll go ahead now and go back to Model, Wall, and I'm going to reduce some of these snap settings. We're going to model from column to column using just snap to endpoint. That's the minimum requirement in terms of the snapping that we need to snap from column to column. So now we have again something that looks like that. Now the walls are referenced from plane to plane, they're not referenced from the same plane. So if we wanted to properly account for the walls carrying this slab on the bottom, that slab also should be referenced from the level below. We're going to go ahead and take this slab, and I'm going to set it as the reference plane 11 with a vertical offset of 0. We're working on reference plane 12. If I move down to reference plane 11, you can see we have something that looks like this. Make sure we save that. This should be reference plane 11 with a vertical offset of 0. I snapped on the wrong slab previous. This should be set to 0. I'll move that. Notice that the other main slab body for the deck is actually pushed down below one level. I'll go back. That was the slab I had inadvertently selected, so we'll change that back to reference plane 12. That moves back up top here, and then down below we would have the this slab below. And this slab actually goes away in this case. So we have something that looks like that with this. This requires the model to be performed in global mode, because if I perform this in single level mode, there's no slab at the bottom of these walls. Those walls just get supported, and this becomes essentially an opening. We will now just mesh the entire structure, because we're going to run the model globally in multi-level mode. So I'll go back to analysis, and I'll mesh this. I'll mesh this at just a greater distance for the slab elements We'll go from 3 to 5. I need to eliminate these duplications here. So I'll delete that slab. Go back up to that level. Okay. Go ahead and mesh the model. And we're going to now run the analysis globally. So the analysis is done for the global run. I'll go and just navigate to the top level again. And if we look, for example, at deflections, in this case, at the top level, obviously the slab is not shown there. I'll have to go down one level to update that deflection. Globally, I could see this if we go, for example, to the analysis viewer, where we have a global perspective of the deformation, and we're looking at Z direction here. And I'll just turn off the values for the contours and the frame elements. And then I'll use this 3D option to show the deformed shape. So we have that same model that looks like this now. Now if you have a similar condition where the story height is short, you could model, again, walls in lieu of the beams with some of the restrictions we've discussed earlier in the video. But it would require you, instead of running it in single level, even though the model itself may only be one level, it requires you to run it in multi-story mode. If you have any questions, please contact us at support@adaptsoft.com. Thank you.